Okay, well, we had a lot of fun talking about NICs, open time servers, PTP profiles, and now we get to have some fun talking about oscillators. So this talk is specifying oscillator holdover for data centers, and I'd like to thank Nazar Jasinski for helping create the material and the slides that I'm about to present. So the agenda is, we have this fourth work stream at OCP-TAP, that is the oscillator workstream, and its main goal is to define classes of oscillators, but not just classify oscillators, also is to specify the test methodologies, and that's what this talk will be focusing on. So we'll focus on the holdover test methodology, which is when you lose timing to the upstream network, and we'll talk about the input requirements, and then a very broad, high-level overview of the methodology, and then finally conclude with a call to action. So here you see in the diagram the familiar network topology where we're illustrating there's different nodes of timing. And generally speaking, the source of time is a GNSS satellite, so it's atomic clock. Typically there's two cesium redundant clocks in the satellite. And then as that timing propagates through the data center, at each node it could be impacted. And the goal of the OCP-TAP is to enable this time stamping or time certainty at each one of these nodes. And they'll all have different levels or different classes of oscillators at each node. And so our goal in the oscillator workstream is to dictate, to simplify, to make it easy for vendors to select these oscillators in terms of stability requirements and in terms of holdover. And part of the effort in the oscillator workstream is to define the holdover time, which we're going to call tau sub h. And also the window of uncertainty, or time error bound, is very important in the end application. So the server will need to report that to the application always, basically, continuously reporting this window of uncertainty. And so this places somewhat of a burden on the vendor to actually select the oscillator. And the problem that we're trying to solve is today, if you go on the manufacturer's websites and you look at the oscillator datasheets, it's very difficult to understand from the datasheet specifications which oscillator would work at which node. And also the holdover requirement, which is when you lose connection to an upstream master, then it relies on the local timing of the oscillator to hold over the accurate time. Holdover methodology is not standardized in the industry, whether it's data centers or any other industry. The way you test and specify holdover is different for every manufacturer of oscillators. And so this is a fairly ambitious goal that we have here in the oscillator workstream, which is try to specify a holdover methodology. And that's what I'm going to be discussing here. But once we do that, then you'll be able to compare different oscillator vendors' data sheets, apples to apples, or at least their compliance report to the OCP-TAP specification for oscillators. You'll be able to compare them apples to apples, and there'll be full transparency in how the holdover was measured. And that's really the end goal, is to enable a very easy selection of oscillator when you're giving a lot of variety of oscillators. So the holdover test methodology. This is a very high-level overview of the visual model of holdover. And this is illustrating the key contributions. There's really three key contributions. On the upper left, we have the frequency versus temperature plot, and we're zoomed in between temperatures T1 and T2. And let's assume our application is varying in temperature between T1 and T2. The frequency is going to change as a function of temperature, and then that's natural for any oscillator. And the more money you pay for an oscillator, the less variation you're going to have, but there'll always be this noise contribution during holdover. And then if we accommodate the variation in temperature, which is the center left block in red, we're showing the temperature variation in time during holdover, and that'll translate us to the lower left block, which is showing how the frequency changes as a function of time. And then we're going to add that to the other noise contributions, which is on the top. We have daily aging. So as the oscillator just essentially sits there operating, It's going to be relaxing the mechanical stresses of the package, the way the package gets soldered onto the board. It's going to be relieving stress over time just naturally. And all these things will translate into changing the stress on the resonator that's generating the time for the oscillator, and relaxing it over time is going to lead to a change in frequency. So this is a second noise component. Then on the bottom we have wander, which is the natural variations, the random variations of oscillator noise over time. All three of these things add to provide some variation of frequency versus time, which when we integrate converts frequency into phase, which we can do a unit conversion to convert to time. And then we can see how that relates to time error versus time, and then we can have some limit, for example, 1.5 microseconds, and so on. And this is sort of the model that we're using for holdover at a very high level. There's 3 noise contributions. Yeah, so OCP-TAP is going to specify the following parameters as part of the test methodology. These parameters are the parameters that if we didn't specify these parameters, they would create a difference between when one oscillator manufacturer measured a component versus another oscillator manufacturer. So by specifying each one of these parameters, we're going to ensure apples-to-apples comparisons between different vendors. So the standard will, of course, specify the holdover time, the maximum time error during holdover. So that means that we need to specify the actual holdover time. We also need to specify the thermal profile that the oscillator will experience. And this will mean that we need to dictate the starting temperature, the ramp rate, which is how fast the temperature changes over time, and then the soak time, which is how long the temperature sits fixed for a certain amount of time. And then we have the operating ambient temperature range. This is the ambient temperature the oscillator experiences during the normal application. And then the next 2 bullets, we're talking about specifying the actual ambient temperature that we're measuring daily aging and measuring wander versus time. And then probability of error. Every system has a maximum probability of error that it can live with. For example, if the probability of error of the application is 99%, that means we have 1% failure. But more likely for a data center where we want to see 6 nines probability, which is like 1 micro percentage of error. So this has to be specified by the system because we're dealing with random events, we're dealing with statistics, so we need, in our model, we need to understand how much probability of error the application requires. And then we have the training time for the oscillator before it enters holdover. This is the time that the oscillator is learning by being locked onto the network. And then when it disengages from the network and it enters holdover, then it's going to have a certain initial frequency offset. So this will impact that value. And then we have the number of units in a population. So in general, when people talk about holdover, they talk about it in the industry as holdover for one device. But in OCP-TAP, we want to quantify it for a particular product line. So if SciTime or another company is selling you an oscillator, we want to be able to report for that family of oscillators, and we ship you, millions of units, hopefully. How many of those units are going to be within our specification? So in order to do that, when we create this methodology, we're going to specify the number of units that we need to test, and that's the capital value N. So that's the sample unit population. For example, part of the methodology for testing holdover will be us specifying the standard. We need to use 10 random parts from each of 3 lots, where each of the lots have a different process and assembly process. And that'll create some variation that we should be able to quantify the maximum impact of these oscillators in the specs. And then there's also a trial population. So not only is there a sample unit population, there's a trial population. Because if we were to measure one device over and over and over and over, we're going to get different answers, because there's a random event when we're characterizing frequency stability. So we're going to capture those random events using capital M. And then finally, some systems compensate for daily aging. And if they do, then we need to know that so that we're not counting that against the oscillator. So these are the inputs. The inputs will define will enable us in the methodology to ensure an apples-to-apples comparison. So the actual methodology itself requires a few things to be measured. It's requiring frequency stability over the operating ambient temperature range to be measured, and it requires a frequency versus time at a constant temperature. Or when I say constant, it's roughly within 2.8 degrees Celsius. There could be some variation, but it's fairly constant for some time interval. And let's just say whatever the holdover time is tau, we want to go 12 times that to get good statistics. So if we measure those two things in the lab, then we can compute from that the daily aging and the wander, and use those in a model that I'm going to show in the next few slides to calculate the maximum holdover time. And that maximum holdover time is going to assume a Gaussian distribution for the noise processes. So there's 3 noise processes, really. There's aging, there's thermal wander, and there's wander. And there's really 2 components of wander. There's the wander during holdover, and there's the wander affecting the initial frequency offset when you enter holdover. So with those 3 components, if we're making the assumption that they have a Gaussian distribution, and from those Gaussian distributions, we can pick off the mean value and the standard deviation. And then it's up to the oscillator manufacturer to report what the maximum time error is at a given holdover time, tau sub h, and also if there's any special conditions that they have for that are vendor specific. For example, if the vendors require you to place a cover over the oscillator, or if they request certain mechanical design restrictions of where you can place the oscillator. These are the things that could impact the results when they do their measurements, and in order for you to reproduce the same results in your laboratory, you would need to know those things. Okay, so our model for computing the maximum time error is going to look at the Gaussian distribution, and it's going to sum the means and root sum square the standard deviations. Essentially, yeah. So this is a very general statistical approach for working with Gaussian distributions. And the math looks fairly complicated here, but actually it's fairly simple. If you just think we have multiple independent random variables, and they all get added together, the end result is going to be a random variable whose mean value is the sum of the individual noise components, and whose standard deviation is the root sum square of the individual standard deviations. And that's all that this equation for Emax is telling us, except we have to account for the maximum time error, and that means we need to have this crest factor Q sub x, which converts the standard deviation, which is an RMS value, into a peak deviation. And there's really 2 possibilities for this crest factor. If our final time error distribution is centered around 0, then the distribution that's leading to the maximum time error, which is shown in the rightmost column, could have errors generated either on the most positive side or the most negative side, and they're equally likely because it's a Gaussian distribution. And so in that case, you'd have Q sub x is equal to Q sub 2 for a 2-sided distribution, and you would pick off your value here for your crest factor. So if you're interested in 6 nines statistics, then you would pick a 4.892 value for your value of Q sub x. On the other hand, if your distribution for total time error, resulting from all the noise processes, is not centered around 0, but is offset from 0, then only half the population is involved in calculating the maximum probability of error, because the P sub B is displaced to the right in the example I've shown here, and so it's going that's going to dictate the maximum time error. And then the value slightly reduces from 4.892 to 4.754, and we would simply use this lookup table for the particular probability of error defined by the system and substitute that into the equation, and that converts our noise processes into a maximum time error. And the interpretation of this maximum time error is a little bit different than what the industry is doing today, because today we're talking about, the oscillator manufacturers are talking about, here's the time error for a unit that we measure. But what we're actually trying to do in the standard is say, for that product family, this is the maximum time error that you can expect with this given probability established by the system. And that's PCB dictated in the standard for different use cases. Okay, so there's a lot more slides that are here, more as supplemental information that I don't really want to go into. There's a lot more details about how we calculate time error from each one of those subcomponents, those noise processes. So the call to action is going to be, we have an oscillator workstream, and this standard, the way I've proposed it here today, is not finalized. So we would like to solicit feedback from the industry to participate in the oscillator workstream. And next week, as part of the main OCP-TAP work group, we are going to give an overview of the oscillator workstream. So we encourage everybody to attend the meeting next Wednesday. We'll go over this and other aspects of the oscillator workstream, and we invite you to participate. If you'd like to join the oscillator workstream, please contact myself. My email is in the OCP-TAP wiki page. And there's a lot, all of the oscillator workstream meetings are online, and the links are in the OCP-TAP workstream. Every meeting that we've held has been recorded on video and is available for you to review if you'd like. So thank you very much. Are there any questions?
Thank you, Gary, also for the great work that you do on this workstream, this extremely technical formulas. I want to ask if do you see any difference in all the characteristics that you mentioned between an O6O, a T6O, another XO, or it's just formula and the difference will be in the number itself?
Yeah, there are differences between the different types of oscillators, but where they would show up in this model is, you'll be trading off different subcomponents, different noise components. And so while those noise components will change the way that you add them, as long as they're following a Gaussian distribution, which we're assuming they are, then it'll just show up in the numbers, as you said. Yeah, so, but yes, definitely the way that they add up should all be consistent. Yeah.
And you're going to, the intention is to divide those results into classes after market data will come back with those results?
Yeah, so what we need to do next for the test methodology is actually prove out the physics that we've outlined here. So we're going to go through, and it's going to take several months to actually measure different classes of oscillators and prove that when we measure the actual holdover, it agrees with our model predictions. And when we do that, then we have a straightforward methodology to test holdover. In addition to that, we'll have a separate set of specs that are for the classification of oscillators. So the classification of oscillators will identify all of these inputs to the test methodology. Those will be called out in the standard, but then the test methodology itself will be a separate part of the spec that doesn't have these parameters in it, but use it as inputs. And then those will be two separate documents.
And I have one last question, sorry. So this data center is an emerging market, and for those accurate oscillators, this is a new market, actually. Do you see that oscillator companies could leverage that in their traditional markets? So there is maybe a better motivation for them to come and join, or everything that they're going to do here, if they will join, will serve them only in data center?
Yeah, I definitely see a motivation, at least within SideTime, and I would expect with other oscillator vendors. We do have other oscillator vendors working within the oscillator workstream. And over time, there's always a demand for better time synchronization, better accuracy. And so that'll dictate that the different types of oscillators will become, the more accurate oscillators will move more into the data center as these applications develop that require them, and that'll generate more interest. So I do see this snowballing, and we're at the very beginning of it right now.
Thank you.
Thank you.
Okay. Yeah, this gentleman mentioned it's the last question, but actually I'm the last, probably. Okay, so I saw your slides when you do the calculation for the error measurement. You adding all those kind of the factors error together, right? From agent, yeah, that's it. From agent to the temperature to the other random, all those kind of the factors. Each of them are different kind of the variables, right? So when you do the mean calculation, I did not go through the math yet, because suddenly show up with this. So I'm just wondering, is simply just adding all those kind of the mean together linearly, and also with the standard deviation square root adding together without the weight, is that the real realistic, practical modeling for the oscillator's performance?
So your question is, do we need to weight each of the distributions differently before we add them up?
Correct. Yeah. The reason, because each of those kind of the factors impact oscillator for the holdover actually is different. So if just simply linear adding may cover, the one factor override another factor's impact with the oscillator performance.
Yep.
Thank you.
My understanding is that it does add as shown, because it's just traditional Gaussian statistics that we're adding up. Yeah, so I haven't...
I can maybe chime in here. Hi, Ladwin here. I think that is a nice question. At least I don't know the answer to. And sorry, your good name?
Oh, my name is Zhao Chun.
Nice to meet you, Zhao Chun.
Huh? Oh, the company I'm working is Recon.
Oh,
we are
okay.
also the oscillator.
Yeah.
But we are friends.
Oh, nice to meet you then, and thank you for coming to our session. We would like to encourage you to attend our workstream.
Okay.
So that's a challenge. Please come to our next workstream meeting. It's every Wednesday at 8 a.m., run by Gary. And I think we can have a deeper discussion over there. We simply ran out of time, and we want to hear your answer.
All right. Thank you.
Thank you.
Thank you for the question, though.
Gary, thank you so much.
I'm all set. Thank you.